All right. So I guess I'll start. Thanks for coming, by the way, to this session. I'm GM Harshvardhan, and I'm a core member at Cord, and I'm pursuing my master's in artificial intelligence from Boston University. So today I'll be talking about why cross entropy loss is so important in classification and how it is derived from maximum likelihood estimation. Um, So a quick note, this session was also supposed to cover intro to Bayesian inference, but while I was making these slides, I realized that it would be a lot to absorb in a 30-minute session. So maybe I'll cover that in some other session in the future. Also, another note before we start is this session can get a little math intensive. So if you start to see those symbols, those math symbols pop up, try to pay a little more attention so you don't get lost in the process. But I'll keep things short and simple and try to go as slow as possible. Um, so basically, I was this guy, right? I used to use C loss a lot, cross entropy loss, but I could never know why I was doing that. Obviously, I knew that it gave me empirically the best results, and also that because everyone else uses it and it's so popular, and there is no other loss function that I knew about except for something like hinge loss or very niche losses, and that is why I use it. But I could never explain why this is the case. I mean, did someone just come up with this function and now we're all using it? So what if I come up with a function tomorrow and it's better than C loss? Is there a mathematical proof to why the C loss has that particular expression, or why does it work so good? So I'm actually surprised that many machine learning courses today they don't have explanation of how this loss came from, like where it came from and how is it derived. And I'll be covering that today. And it's derived from maximum likelihood estimation, which I'll give a brief intro to first. So consider a data set like this, right? You have your independent vectors or independent features x1 and x2, and you have this is the distribution of that, and you have the classes. So one class is a blue cross and one class is a red plus, and that's your dependent feature. So let's assume that we have this data, right? And I'll represent it in this way. So you have the data in x and the labels in y, and x is a vector, mind you, because x has two components, x1 and x2. So now we want to fit a model with some parameters theta for binary classification, right? So if you're unfamiliar with the term parameters, so if you are new to machine learning, you might know linear regression. So parameters in that case would be to find the coefficients of each of the vectors that you have, or each of the independent features that you have, so that you can fit the data. So those coefficients are your parameters. And if you've dealt with neural networks before, the parameters in that case are the weights and the biases that you want to find. Basically, in machine learning, we want to find these parameters for any data set so that we can fit the data well. So now in maximum likelihood estimation, we want to maximize the probability of observing this data. And initially we assume that this data was generated by some parameters, right? Now that's a lot of things, like what I just said. Let's go back a bit. Um, so I said we assume that this data is generated by some parameters, right? We assume that there is a prior set of parameters that generated this data. And ideally, in machine learning, we want to find these parameters. So in the future, when we have a new data point, we can classify it, right? Or we can do regression with it. So now we know that we want to find those parameters. And how do we do that? We do that by maximizing the probability of observing this data. Now, this doesn't make sense at first. What do you mean by maximizing the probability of seeing this data? It means, so if say there are 100 points here, right? Then they're not really 100 points, but just assume that there are. And if you have those 100 points, right, there could be so many possibilities of seeing so many data sets. So for example, this point over here, you see, this could be a blue cross, right? Or this could be a blue cross. Or maybe on this side, this could be a red plus. and so on. So there's so many combinations possible, right, for those 100 points. So what is the probability of seeing this exact data set out of all those combinations, right? And we want to maximize seeing this data so that we can then extract the parameters theta from it, right? So the process is simple. You maximize the probability of seeing this data, and then once you do that, you extract the theta that comes out of it, and that's it. That's your parameters, right? That is what maximum likelihood estimation does. So that this statement is just reiterating it. Maximizing the probability of seeing this data will help us extract theta star. Theta star is the optimal parameter set that we want. So if I go through this mathematically, it'll be a little clearer. So if you have the data set, right? If I represent each point with u of I, right, and u of I is this basically x of I and y of I, then my data looks like this from 1 to m if I have m training points. Then all this like don't look at this, right? I'll actually explain this in words before I go through this. So um, what do I mean by finding the likelihood? We want to maximize the probability, right? So how do you do that? You basically find the likelihood and then you maximize the likelihood, right? Now what is the likelihood here? Likelihood refers to basically a product of probabilities, right? So you basically have this point, right? This point, you get the probability of seeing that point, you multiply it with the probability of seeing this point, and then so on for all the points in your data set, right? And that is your product of probabilities that gives you a likelihood. And this is exactly that. This product is going from I1 to M for all the training points, and you have all these training points in U of I. You're getting the probability of that, right? And theta is just the distribution, how it was generated, the parameter of the distribution. It is parameterized. This probability is parameterized by theta, right? So this is just a product of probabilities, and that's what gives you the likelihood or the probability of seeing this data, right? And like I said before, we want to maximize that, right? If we do that, we can get theta out of it. So argmax here, you argmax refers to maximizing a function, but with respect to a particular argument or with respect to a particular component of the domain. So basically, this means that we are maximizing likelihood and we are extracting theta out of it. And that theta would be the optimal parameters that we want, or theta ml, which means theta maximum likelihood, right? And this theta is all we need for fitting the data. And this likelihood expression above, it can be written like this if you want to maximize it and get theta. And if you take the log on both sides, this product will become to a summation. And this is how it will look like. And this is important for later. It's just another way of writing the same thing. Um, Also, quick note, I'll take the questions in the end. I know a few people have posted them because this presentation will require some flow of thought. If I interrupt in between, then maybe it'll be a little difficult to come back to. So I'll definitely look up all the questions in the end. Thanks. Um, yeah, so again, this is the data likelihood. This is the log likelihood. So these two terms are very, very like used very often in machine learning, or at least in generative modeling, where you are trying to maximize the likelihood of data. For example, variational autoencoders do that, and GANs don't do it, but they do it implicitly. They don't maximize the likelihood; they minimize the cost function. But I'll show you in the later slides that it's basically the same thing. Um, and theta ml is your optimal parameters, theta star that we wanted to extract before. Um, Also, yeah, if you're unfamiliar with argmax, it just means if argmax of fx, you see, it means what is the x where fx is the maximum, right? It's not just fx where it's maximum, but it's the x where fx is maximum. So we're getting the theta where this function is maximum, the likelihood function. So in general, right, in machine learning, we know that we have a training set, we have a cost function j, and we want to find theta with minimal cost on training set, right? And this is our model here, the hypothesis with some parameters theta, and we have input x, and we want to predict something like y. Now, alternatively, what MLE presents is instead of the cost function, you can have your data likelihood, right? This is the data likelihood for all the points for all I. And you can find theta with the maximum probability of the training set. Instead of minimizing the cost, now you can maximize the probability of seeing this data, right? And that is an alternative view presented by MLE, which I was actually, well, this was my reaction when I saw this, um, because I used to think of machine learning as this, right? But seeing such a simple explanation of MLE and how it is an alternative to that, it just opened my eyes as to like so many possibilities could be possible with well machine learning. So so I think that was very surprising to me and very exciting in a way. Um, so going further with this, how can I apply this now to derive our loss function that we have come to know and love so much? Um, so cross entropy from MLE, right? Uh, so I'll set up a binary or actually a general classification setting here. So you have your prediction h of theta given an input x, which is the probability of getting class one given x. So let let h theta of x be your probability of class one. That means if if the class is zero, then you'll have one minus of this, right? So that is what is written here. P y given y equals zero given x would be one minus of the class one, and this is pretty simple because now we're dealing with binary classification, and you have model parameters theta, right? What is the probability of observing a data point, x1 and y1? And by this, I mean, for example, this may be x1 and y1. And what is the probability of observing this one data point? Suppose you had only one data point, right? So the probability of that would just be the multiplication of both cases, right? What both cases? In the binary setting, so class 1 into class 0, right? This is class 1 as shown before, and it will be raised to y1 or the label, the value of the label, and multiplied by 1 minus or multiplied by the 0 case, if multiplied by the 0 case to the power of 1 minus y1. So what is all this? Like what is happening here? So it's just a fancy way of writing the actual probability of a class. So for that point, right? That point was a blue cross, I think, right? So in that case, you'll only have one term. In every case, you'll only have one term because the other will get zeroed off. So for example, that was say class one, right? Blue cross is a class one. Then y1 becomes one, and this one minus y1 becomes zero. So this thing will vanish, and you'll have only this thing for class one. If, for example, it was a red plus, then you'll have one minus this thing, this whole term. This will remain, and this thing will vanish off because y1 becomes zero, that is class zero, and one minus zero stays as one. So you have this term left. So it alternates between these two terms depending on which class you're dealing with, right? If that's clear. Now, if that was for one point, right? If you have the whole data set, if you want to get the probability of seeing that whole data set, you just have to multiply all the points, right? All the probabilities. You just have a product over here from I1 to M. And this is again the data likelihood, which I can write as probability of data given theta, right? Now, we want to maximize this probability and extract some parameters theta ml or theta star, right? As I said before. So going forward with that, um, now it's the same expression as before. We know that theta ml is the maximum of this data, of this function over here, the data likelihood, and we get the theta out of it, right? So it's easier to maximize by taking a log because here you have a product, right? If you take the log on both sides, this product will become a summation, right? If you do that, it's easier to maximize any function. So if we do that, this is how it will look like, and it starts to become more familiar. Like if we are more familiar with this now because it's starting to look like cross entropy. Basically this y comes down outside because it's in the power, and then this is the log of h theta xi, because this is h theta xi, and the same for the other term you hear. This comes down, and then you have log of 1 minus h theta xi, which is 1 minus probability of seeing class 1. Um, so this is how it looks like. And either you can do that, you can maximize this function, or you can minimize the below function. So if I multiply both sides by -1 over here, right, then I can minimize the whole thing to basically do the same thing. If I'm maximizing this, I'm minimizing the negative of that, right? Intuitively. And that is what's called the negative log likelihood, right? And this is very like this term is also very like very much used in machine learning, the negative log likelihood. And if you see, that is cross entropy loss derived. This is exactly the form that it takes, at least for binary settings, and that is how you derive it for classification. And I think there is a little the this expression is a little different for categorical. This is how it looks like. Basically, as I said before, it is alternating between the two classes, right? If you have many classes, it'll only take one class, which is the y, which is the yj, right? If yj is one, then this thing will be evaluated. So that's for categories. And that is basically the derivation of MLE from cross entropy. If you have anything to share or any questions you have, any questions, you can just put them in the chat. I'll just look over them after the end. But there are two parts to this presentation. We just saw why cross entropy works for classification, right? Now I want to extend that to seeing how cross entropy works for neural networks as well, um, because today we do a lot of deep learning and classification. We do a lot of classification, and mostly I think all of the state of the art systems even today use cross entropy, right? Unless they have a custom loss function for their purpose, but in general it's cross entropy. So I'll take a toy example, right? um, I'll compare the cross entropy loss with another loss, quadratic loss, and I'll show how it is expressed as mathematically. But I'll compare the two for a single neuron, right? I'll take one neuron and I'll make it learn to map an input of 1 to a 0, right? So if you give it a 1, it should learn to say 0 as the output. So consider that the activation is sigmoid, and it takes a z, where z is the wx plus b, which are the weights and the biases, right? The w and b are the weights, and b is the bias. So now I have a little animation here, which I hope you can see. So if you have the quadratic loss over here, this is how it looks like. It's just a square loss divided by 2. Where y is the output and y is the target and a is the output. You can see here that the neuron is adjusting the weight and the bias to to minimize a cost function, which is this one, right? And the output is going from 1 to a 0 as the epochs go further, right? And just notice a curve over here, right? It initially it doesn't learn a lot, and then it learns like it learns very fast after a point, and that is for quadratic. And if you take the case of cross entropy on the right side, you can see that the cost is decreasing quickly since ever since it started training, and the weight and the biases are at optimal values very quickly. There is no problem of this learning slowdown initially, as was the case with the quadratic cost. Now, why does this happen? There is a reasoning behind this, right? I'll show you that reasoning mathematically, and I'll explain why that proof is why it makes sense, basically, right? It's not just maths, but it's also intuition. So if you're not good with maths, don't worry about it. So yeah, why does this happen, right? Now, we know that the cost function for any neural network is actually adjusted. In fact, the cost function is evaluated and it is used to adjust your weights and the biases, right? And that is written over here. The partial derivatives of j with respect to w and j with respect to bias, they determine the speed of convergence of w and bias, right? So if these partial derivatives are very large, then the speed of convergence or speed of change or the rate of change of w and b would be large, right? So if that basically means that if I change the weight, how big of a change will it have on the cost, right? If it's very large, then I can change the weight slowly to have a large change in the cost function. Now the problem here is, um, for both of these cost functions, these two values, these two partial derivatives are different, right? Which causes this behavior. How is that different? So if you take these cost functions on either side, right here, on the left side you have quadratic, you can differentiate the quadratic function with respect to w, right? If you do that, you get first you differentiate the outer function, which is like the power of 2, and then you differentiate the inside. So you differentiate a first, and a is basically, if you remember, is the activation, right? Activation of sigmoid. So sigmoid prime here, the sigma prime here is basically the differentiation of sigmoid with respect to w. And then if you actually differentiate z with respect to w, z was wx plus b, right? I'll just show it again. Z was wx plus b. If you differentiate this with respect to w, you get x. That's why you have that x over here. And for simplicity, because we had in our toy example, x equals to 1 and y equals 0, this thing is basically the same thing as this on the right side, which is the activation times the sigma prime. But that is not so important. In general, this is the case always, right? It doesn't matter what our values are. This is the general case that you see this expression when you're differentiating the cost with respect to the weights for quadratic. And pay attention to this term over here, which is a sigma prime, right? This is going to be important. So remember this. And yeah, and for the bias, you have again the same similar expression. Not going to go over it again. The differentiation, um, and you have that sigma prime term up there as well, right? Now let's move to cross entropy. Um, so the cross entropy is the gradient of cross entropy, or the derivative of cross entropy with respect to the weight or the bias. Um, the differentiation has a lot of steps, and I have skipped that. So I hope that's okay, because it would be a little boring. So if you differentiate this with respect to the weight, this will be the expression you end up with, right? It's the input times the output of the network, which is the activation over here, and it's subtracted with the target, right? Notice that there is no differential over here, as was the case with quadratic, right? And it's just the difference of magnitude of the error. Basically, it's just the magnitude of the error, right? It's the output minus the target. So this is basically the magnitude of error, which determines this partial derivative, right? That is also important to keep in mind. And it's the same for the bias as well without the X term. Now, given that we now know this, how can we map back to the original question of this learning slowdown? What we just saw, how does it like relate to this, right? So let's see, in the quadratic case, we know that the sigmoid function looks like this, right? And we also know that if you try to find the gradient at, say, x equals 2 or 4 or anything like that, that's higher, like on the positive side, the gradient would be very small, because look at this, this is very flat, right? So now at when the z is higher than 1, for example, the gradient sigma prime is very low, right? And because of that, this thing becomes low, right? Initially, as you see, the wx plus b, this value would be greater than 1, right? Like over here, right now. So because of that, this value will become low, and because of this value becoming low, this whole partial derivative becomes low. So that means there is not a lot of the rate of change of the cost is very low for any change in the w or the bias or any parameters, right? So that is why you have a very slow start initially for quadratic. So this is the slow start that you see. Now, cross entropy doesn't actually, it's very beautiful, right? Cross entropy is very beautiful because once you derive it, once you see the partial derivative of it with respect to the parameters like this, you see this expression, right? So first of all, it avoids this differential first, right? So there is no problem of the gradient being small, which results to a slow learning rate, right? So and the other thing to note here is that it is proportional to the magnitude of error, right? So as humans, intuitively, we would want to learn the most when we're the most wrong, right? So if the error is too high, we want we want our neural networks to learn the most, like to quickly get rid of that error. And this is exactly provided, what is it provided by cross entropy with this term over here. So the rate of change of parameters, in fact, this should be cost. The rate of change of the cost with respect to the parameters depends on the magnitude of the error, right? So the higher the error, the faster the learning, and that is basically what we want in any any setting, any classification setting. Um, and I think that is pretty much it. Yeah. I'll go with the questions now, but I hope you understood a little bit. If you could absorb anything out of it, that's enough, because you don't have to delve deep into the math. You just need to know where things come from, so you are more comfortable with using stuff like this, so that you know if someone asks you, you can say that yeah, there is actually some mathematical proof behind it or anything like that. So you can never be confused about that or unsure about it. And why cross entropy works for neural networks is also um, very evident, that you have this learning slowdown problem with other with maybe other loss functions like this one. And again, if you combine cross entropy with ReLU, the learning becomes even faster, because ReLU also in a way ensures that the gradients in your network, they don't vanish, right, as compared to say sigmoid activations in the middle layers, because sigmoid again has this problem of gradients vanishing at extremes. So you have that in activations as well, not just loss but also activations. Yeah, I think that's pretty much it. I'll stop sharing my screen, or actually I keep it, but I'll look over the um, questions. Okay. Why negative log likelihood is CE, not maximizing the argmax, and you should be taking the negative. Okay. So I think you referred to this slide somewhere. This one, right? So you asked why negative log likelihood is not CE. It is CE actually. If you take this term over here, this is the cross entropy loss that we know, right? This is negative log likelihood. Um, so not maximizing the argmax, any intuition behind taking negative. Um, I'm not sure exactly what you mean by not maximizing the argmax. If you could elaborate on that, that'd be great. But the intuition behind taking the negative is because we want a cost function, right? And intuitively, a cost function, you minimize a cost function, right? You don't want a lot of cost. So if you don't take the negative, um, you end up with maximizing this function. And in reality, you are more familiar with minimizing something, which is a cost, instead of maximizing it, right? So you can take a negative and basically say, I want to minimize it now, because that's the same thing as that. Plus, I think the negative also comes from more mathematical perspective. It, the entropy that we know, entropy between two distributions P and Q, it always has a negative sign. And I'm not going to prove or derive the formula of entropy now in maths or in information theory, but there is a negative sign in there as well. So this thing is not entropy. The below thing is entropy. And this is, I don't think we can even call it cross entropy. It's just a step in the process to getting to cross entropy. uh, yeah, I hope that answers your question. If there are any other questions, please let me know. um, Seeing the lack of questions makes me nervous, because I'm not sure if it was too difficult to follow or anything like that.
Yeah, GM.
Yeah, who's
Actually,
this? Yeah, Balaji.
um, so can you tell like how to go from parameters to the dataset?
From parameters to the data set,
Yeah.
um, you always go from the data set to the parameters in maximum likelihood estimation.
So
um, can you give an
how?
example?
No, I'm asking you like the example. Like,
Oh, you want, like, okay, so you have the parameters, you want to make a data set out of it, right?
yeah.
Okay, cool. That's exactly generative modeling. That's what generative modeling does. So so wait, if you have, so you're basically flipping this thing, right? You're basically
Mm.
saying you have the theta. In fact, um, wait, you're not flipping it. You're saying you have theta and you want the data, right?
Yes.
Yeah, cool, cool. Right. So that I think that is exactly what I was going to cover today with Bayesian modeling. So
Oh, okay.
Bayesian inference basically specifies a prior over the parameters. So, okay, so you have the parameters initially, and then um, you get, as you get data, you can adjust those parameters according to the data, right? So you can have like a better
Mm,
model than even MLE. Like MLE assumes that this is exactly the distribution, right? But if you have a prior, so for example, the prior over here could be two Gaussians, right? A Gaussian over here and a Gaussian over here, right? For the two classes. So that's a prior that I'm setting. And then that those Gaussians can, like, they can adjust with every data point that you give it, so that the parameters actually fit the data the best, right? um, and they also have like more room for error, so it's like very regularized instead of very, being very um, concise, and that can lead to overfitting because you are very rigid about your model, which
mm,
actually is which mostly is given by MLE. But you want to have some room for error, which Bayesian inference introduces. Also, in a generative setting, if you have parameters, you can use those parameters in your function to generate more data. Instead of getting data from real world, you have the parameters, right? You can plug in those parameters in your function,
yeah.
and you can just sample from the data space. So for example, I have the parameters now. I have a Gaussian over here, I have a Gaussian over here, right? So I can just pick an x1 and x2, and I can know the class, right? Because I know the distribution, I know
Yeah.
the parameters now. So basically you are
Parameters.
generating data now, right? So that is another way to look at it, I think.
So that's Bayesian inference.
No, this is the second thing I just described was generative modeling. Bayesian inference is knowing what your distribution looks like. So my prior over the parameters now is like there are two Gaussians, right? And they change with new data coming in. The only difference is we are not making data, we are getting data from real life. That's one case, right? The other case is when you make your own data with the parameters, that's generative modeling.
Ah, okay, okay. Yeah, I
Yeah.
got it.
So there are two cases possible depending on if you're getting data from real life, or if you want to generate data given your parameters. Yeah. Right. If there are any more questions, please let me know. Otherwise, you can wrap this up. Thank you. Um, I hope it was not too difficult to follow. Uh, I guess we'll wrap it up then. Uh, Feel free to, hit me up if you have any questions later on, anytime. Like, I'm on LinkedIn or the Slack channel. If you're in Cord Slack channel, if you're not there, please join. It's a great place to be in, among other like very good people in machine learning, like very talented people. Uh, and Yeah, just make sure you join Cord. Even if you're watching this video sometime in the future and on YouTube, um, join the community.